So we are going to talk about an algorithm called the continued fraction algorithm. Let's say you have a set of integers a0, a1 through am. Then I can represent these integers as a continued fraction in the following way. I can write this as a0 plus 1 over 1 plus a1 over 1 plus 1 over a2 over 1 plus 1 over a3 and so on, and then maybe one over am. Now this is a fraction called the continued fraction. And this is the continued fraction representation of this set of integers. Any real number can be approximated by a continued fraction, and any rational number, we can see that there is a continued fraction algorithm that terminates. Okay, so let's take an example of a fraction, let's say 31 over 13. And let's try to represent this fraction as a continued fraction. So what would be the representation of this rational number as a set of integers, which can then be written as a continued fraction like this, right? So the procedure or the algorithm is the following. You write 31 over 13 as the integer part plus the fractional part. This is 5 over 13. So that is the first step. This is the first numerator. So let me just circle this, highlight this. This is the first numerator. This will be the second numerator. So that is the first step. Now what you do is that, so this is the division step. The next step is the invert. So you invert this fraction. So you write this as 2 plus 1 over 13 over 5. Okay, so this completes one iteration, which is the divide step. So this is the divide step. And then this is the invert step. And then you repeat. So now you have this fraction, which you first divide. So this step 1. Step 2 would be to again divide this fraction to convert it into an integer part, 2 plus a fractional part, which is 3 over 5. Then again, I'm going to circle the numerator over here. So this is the divide part over here. And then I invert, which is then becomes 2 plus 1 over 2 plus 1 over 5 over 3, right? So this becomes step 2, which is this is divide and this is invert. Okay, now step 3. So we have come to Now again, we'll first divide. This is plus 1 over 2 plus 1 over 1 plus 1 plus 2 over 3. And again, in the division step, we note down the numerator of the fraction. And then the invert step is 2 plus 1 over so this is the divide step, and this is the invert step. And then one more, step 4. We have 2 plus 1 over 2 plus 1 divided by 1 plus 1 over 1 plus 1 over 2. And we note down the numerator. And this is where the algorithm terminates, because when I flip this, you will get an integer, right? So the algorithm terminates over here. Now I'm going to write down the numerators. So the first numerator is 31, then 5, followed by 3, followed by 2, and then followed by 1. So the continued fraction representation of 31 over 13 is all the numerators. So 31, 5, 3, 2, and 1. Right? So I can take this and so sorry, apologize. This is not the continued fraction representation, but rather if I look at these numbers, right? So this is A0, A1, A2, A3, right? So continued fraction representation is 2, 2, 1, 1. Yeah, that is it. And so it turns out if I look at the numerators, so 31, 5, 3, 2, and 1. Now this forms a decreasing sequence, and it always terminates for a fraction. So always terminates. And the speed at which it terminates, one can say that if, let's say, I want to represent the continued fraction of a fraction s over r, if s and r are order L, can be represented in order L bits, then this continued fraction algorithm terminates in order L steps, and each steps requires order L square basic operations. So the total continued fraction algorithm has complexity L cube. It can be implemented in order L cube operations. All right. Thank you.